Okay, we're here on exercise set 1.2. Its title is Systems of Linear Equations, 2 Variable. Calculator solution using the graphing feature of the TI-84 Plus. We're encountering single point solutions in these exercises. Now, it's recommended before you do this video and these last exercises that you have already successfully completed the first 10 exercises, because we'll be going to some more advanced aspects of the calculator in these exercises 11 through 14. Okay, let's take a look at the instructions here for these. Part A, is the system linear, 2 variables? If not, state this and explain the reason. If so, proceed to answer parts B and C below. B, solve the system using the graphing feature of the TI-84 Plus calculator. Record what you have entered into the y equals edit screen. Record exact answers if you are able to by using the calculator's fraction conversion feature. If not able to do this, explain the reason and then record decimal approximations rounded to 3 significant digits. C, use the calculator to perform an algebraic check of your solution. Record the result. Alright, let's proceed to number 11. Here we are. Alright, how about this system here? Do we think it's linear 2 variables? Looking at the first equation, this equation is in the form ax plus by equals c. A, b, and c are constants. A and b not both 0. So it's a linear equation. How about the second equation? Alright, although the y's appear first, x is secondly, still we basically have the form ax plus by is equal to a c here. This is a linear equation also. So looks like indeed this system is linear 2 variables. Record that. Yes. This is a linear system, 2 variables. Okay, this means we're responsible to go on to part B in this question. Here, we're supposed to be trying to solve the system using the graphing feature of the TI-84 Plus calculator. Alright, well, graphically, this means for a system, we are to find the intersection of all of the individual graphs. Okay, alright, this first one here, to get this to be graphed in the calculator, we first need to solve for y. That is, rearrange this so that y is isolated on one side. We could do that here. Subtract x over 169 from both sides, then multiply both sides by 274. We would arrive at y1 equaling 274 times 1 minus x over 169. Okay, let's go to the second equation. To solve for y, in this case, we just have to add x over 511 to both sides, then multiply both sides by 117. We've got a y sub 2 equaling to 1 plus x over 511 times 117. Alright, with this in hand, it's time to go to the calculator. Okay, calculator's turned on. Let's go first to the y equals 2 edit screen. Here in y1, we record just what we have developed, and that is our y1 is going to be 274 parenthesis 1 minus x divided by 169. Parenthesis. Okay, let's go down to y2, where we have 117 parenthesis 1 plus x divided by 511 parenthesis. Alright, getting started, we might start off with a standard coordinate system that has x-axis from -10 to +10 and y-axis -10 to +10. I usually start there, and to do that, just going zoom standard 6. This will set up this coordinate system and attempt to graph. Okay, looks like nothing has appeared. Now what? Okay, one thing we could do is we could have the y-axis changed so that it will force the graphs of both of these straight lines to at least appear. To do that, we do a zoom fit. Zoom, and fit is number 0, as you may recall from before. Okay, now it appears that there are two lines which are going to intersect. It's going to be off to the right there some ways. We can start now, change the window and just kind of take a guess at what we think might fit, and to the window where we need quite a bit more positive x-axis. This means we need to change x max. Right now it's 10. Let's just try 200. Kind of guessing. Alright, also when we make this change, the intersection may very well go off the display again, so I will also at this time do a zoom fit. Zoom fit is 0. Aha! Just what we're looking for, the intersection of the two graphs. And now let's go ahead and get it calculated with the calculator. We can achieve that by doing a second calculate intersect. Let's see, I like to move away a little ways to see what it is we have going on here. Okay, it's asking if that there is our first curve. We can say yes by pushing enter. Is that our second curve? Yes, it is. We can go enter. A guess. Alright, now here's where maybe we navigate over a little bit to get right where the intersection appears to be, and then enter. Alright, we have this point here, x and y coordinates provided. The question, part B here, wants us to try to provide exact answers if we can. Let's try that. Let's go back to the home screen, second quit, and let's take x, try to convert it to a rational number, basically, or a fraction form of the rational number, and this is number 1. Enter to paste it on the home screen, push enter again to execute the instruction. Wow, there it is. Okay. Pretty complicated looking fraction, but anyway, the coefficients and constant terms of this system were not so simple, so this could be expected. Alright, let's try to get the exact y coordinate. Alpha y. Math menu, fraction conversion, paste it on the home screen, enter again to execute. What happened here? All the calculator did was give back the decimal representation again. No explicit fraction with a integer numerator and integer denominator. What's this mean? Okay, we'll have to explain this in our answer. Let's take this information and go back to our equations. So here's what we can say. Since we actually have only an approximate y coordinate, we'll have to say that the solution is approximately now the x-coordinate we do have exact 458,629 over 5405, And here's the approximation part. Now, 3 significant digits. So 1, 3. Here's the third significant digit. What follows the 6 is a 4, so we do not round up anymore. We keep a 6 just like that. There's 3 significant digits. All right. Now, a little bit of explaining here because we only have an approximate y-coordinate. What's happened here? Well, let's look at this system originally here, and we notice that the coefficients, each is a rational number, and the constant terms, they're both 1. Okay, a rational number as well. Well, when a linear system has a single point solution, and all the coefficients and constant terms are rational numbers, the solution is going to have rational number coordinates. And that's not really a surprise, because when you think about how you solve this manually, all you're doing are adding, subtracting, multiplying, and dividing these various constants throughout the process. So it's not a surprise that such a system absolutely must have rational coordinate solutions in the end. So we might first make a note of that. So we could say, since the system has rational coefficients and constant terms, the single point solution must have rational coordinates. So, why did the calculator fail to provide that y-coordinate? Then, what's going on then is that in the case of the y, the denominator must have been greater than or equal to 10,000. And that's a calculator limitation. When the rational number has a denominator greater than or equal to 10,000, the calculator fraction conversion will not write it as a fraction. It can't. It's limited. So we need to make a note of that. The y-coordinate is only approximate because its denominator is greater than or equal to 10,000 and thus exceeding the capability of the calculator fraction conversion. Okay, so we have that. Now, that brings us to part C, where we want to check our work here. Alright, for this, it's time to make use of those original equations again. We plan to do an x over 169 with the calculator plus a y over 274 and see what happens there. Secondly, we'll take a look at y over 117 minus x over 511. See what happens there. Okay, let's go. Okay, at the calculator, we may decide to clear the screen and look at that first left-hand side of the equation and record it. That's an x divided by 169 plus y divided by 274. Alright, here we go. Great, it's 1. That's one check. The second left-hand side is a y divided by 117 minus x divided by 511. Okay. Good news. We have a complete check. Let's make a record of this. So this turned out to be a 1. Check. And this turned out to be a 1 as well. Check. The solution looks good. We're done. Okay, next we take a look at exercise number 12. Here it is here. Let's begin with part A. Decide whether or not we think this is a linear system, 2 variables. The first equation, okay, although we see a square root of 5 here, a square root of 3, those are, after all, just constants. So this first equation has the form ax plus by equals c, linear equation. Okay. The second equation, here's this pi here, but pi is just another constant. So this equation also has the form ax plus by equals c. It's a linear equation also. Alright, so part A. Indeed, we can say yes. This is a linear system, 2 variables. Or variable, either way. This means we are to try to solve it with our calculator, bringing us to part B here. Alright, to get this to work, we will, as before, we'll need to take in this first equation and solve for y. Alright, so we subtract x squared root of 5 from both sides, and then divide both sides by a negative square root of 3. Let's see, we could have ourselves a y1 equaling 2. We could have x square roots of 5 minus 7 divided by square root of 3. Okay, let's take the second equation. To solve for y here, we could subtract pi x from both sides, then multiply both sides by negative 1, and then divide both sides by 7. We could have y sub 2 equaling pi x minus 17 divided by 7. Okay, looks like we're ready to go to the calculator. Okay, let's go to the y equals 2 edit screen. In y1, we can put our formulation we have. That is parenthesis x square root of 5. Now to put an end to that square root sign, we navigate forward like so. There. And now we can do a subtraction. 7. We'll need a parenthesis. Now divide by and square root of 3. I want to terminate that square root sign there. Okay, let's go to our y2. This is a parenthesis. Pi. Now, pi has its own key directly on the calculator keyboard. It's actually the secondary function of the caret key here. So go second pi. There it is. And then x minus 17 parenthesis divide by 7. Alright, I suppose we could get something started by using a standard coordinate system. Let's try that. zoom, 6. Okay. A single point of intersection. It's appeared right on the calculator display immediately. Let's get it. That means second calculate. Intersect. First curve, yes. Is that our second curve? Yes. Enter. I guess. Alright, let's navigate to the right a little bit here. That looks pretty good. Enter. Okay. Let's see what we can do here as far as recording exact answers. Let's go second, quit. Let's take that X first. And math, fraction, go. Oh, it just gave back the decimal representation. Okay, how about the Y? Alpha Y, math, fraction, go. Oh, also just gives back the decimal representation. Neither coordinate is being provided as a rational number in fraction form. Okay, let's try to explain that. So here, to record what we're going to be able to say for the solution, we'll need to say that the solution is approximately rounding to 3 significant digits. For the x-coordinate, we have 1.9. Now, following the 1 is a 5, so round up, 2. And the y-coordinate, for 3 significant digits, we have a negative 1.5. Now, the 6 there is followed by a 9, so it becomes a 7 when rounded to 3 significant digits, like so. This is conclusive. Put a nice cloud around it. Now we have some explaining to do because we did not provide exact solutions here. The calculator didn't seem to. Let's think about how we could explain this. Let's go back to these original equations here. Now, in this case, look at these coefficients. Square root of 5, square root of 3. Those are both irrational. And then in the second equation, there's this pi. Pi is famous for being irrational as well. Okay, since we have a case where we have several irrational coefficients, we really expect the solutions, any solution, single point solution, to have irrational coordinates. Now, when the calculator is trying to do that fraction conversion, it's trying to provide you with a rational number. In this case, the rational numbers just aren't there. This problem does not have rational number coordinates, so we should not expect the calculator to be providing exact fractions in this case. So let's write that down. First, let's point out, since the system has several, and really it only takes one, but this one happens to have, this system has several irrational coefficients. We expect a single point solution to have irrational coordinates. Thus, the calculator fraction conversion, and fraction, we mean rational number conversion should not be able to provide exact numbers in this case. Exact irrational coordinates. Okay. Well, of course, there's still the issue of maybe there's a mistake that we've made earlier, and plenty of chance for that, as the keyboarding in this case was actually a little bit complicated. So surely we are glad to be doing this part C, which is our check. Now what we do here is go back to the original equations before we performed any of the algebra to rewrite this, and let's take another look at the left-hand side. In the first equation's case, the left-hand side is this x square roots of 5 minus y square roots of 3. We'll see what that turns out to be on the calculator. And then the second equation, its left-hand side is pi x minus 7y. Let's see what that becomes when computed on the calculator. Okay, let's go. Alright, at the calculator, maybe we decide to clear the home screen, clean slate, and let's take a look at the left-hand side of that first equation. We have recorded x square root of 5. Navigate forward, put an end to that square root sign, and subtract y, alpha y, square roots of second square root of 3. Put an end to that square root sign. Okay, cross your fingers. 7. Good news. Okay, that's one check. Let's try the second equation. Left-hand side, we have recorded pi, second pi x minus 7y enter. 17. Okay, we make a note of this, and we have got ourselves a complete solution with check. Here we go back to the recording. So for this first equation, the calculator arrived at a 7, which that's a check. In the second equation, it computed a 17. There we go, completely checked. Great, all done.